All right, Chemistry 3111. Today we're going to start off with section 20.8. So where we're going to start today is with acid chlorides. So we're going to start with acid chlorides, and then from there we're going to go into anhydrides, then esters, and then finally amines. But let's start by concentrating on acid chlorides. And like I told you last class, acid chlorides are very reactive. Okay, in fact, out of all the functional groups that we study in this class, or in this chapter, these are the most reactive. And we said why. We said there's a dipole going towards the oxygen, there's a dipole going towards the chlorine. We talked about orbital overlap. And basically, the bottom line is this carbon is extremely electrophilic. Okay, so it's extremely susceptible to nucleophilic attack. All right, so that's kind of why he organized them in this order in chapter 20. So it says here an acid chloride is going to be synthesized from a carboxylic acid using SOCl2. And SOCl2 has a name. It's thionyl chloride. And I know that you can draw a Lewis structure for SOCl2 because I've asked my students to draw it during various and sundry exams in general chemistry 1, but you end up with something that looks like this. So we have all of our electrons, and there's our thionyl chloride. Now, thionyl chloride, all we do is it's a liquid at room temperature, and so we just add it to our carboxylic acid. That's all we do. It's a very simple reaction, and you end up with an acid chloride, and you also produce this compound, SO2, which is sulfur dioxide. So sulfur dioxide, and it turns out the sulfur dioxide is a gas, and so where does it go? It goes up the smokestack, out the window. And so based on Le Chatelier's principle, this helps drive the reaction forward, right? If we remove this, it's going to push the reaction in the forward direction. And so, and this is not a joke, but when I used to work as a researcher full time, sometimes we would get new students, co-op students who are coming in for a semester of, learning the ropes of what it takes to be an organic chemist in the lab. And one of the first things that we would ask them to do probably would be to make an acid chloride. Why? Because this reaction works so well. All you have to do is add your carboxylic acid to your thionyl chloride. You watch the bubbles, right? This is it's a gas, so you see bubbles forming. As soon as the bubbles subside, it means the reaction has been completed and you have your acid chloride. Now, like I also told you last class, if you take a simple acid chloride, like acetyl chloride, this one here, so this is called acetyl chloride or acetyl chloride, depending on who you ask, right? Potato, potato. If you take that compound and you put it in water, I said it reacts so violently that it reacts like a gunshot. It'll make a bang sound. Well, if you take any acid chloride, meaning if you have any R group, it could be a methyl, ethyl, propyl, isopropyl, phenyl, whatever. Any acid chloride, if you put it in water, it's just going to hydrolyze the compound and convert it back to a carboxylic acid. Okay, now there isn't a whole lot of synthetic utility to this reaction. Because usually acid chlorides are made from a carboxylic acid. So why you would convert an acid chloride to a carboxylic acid is kind of beyond me. So in my notes, I wrote no synthetic utility, but we'll just write little synthetic utility. Okay, little synthetic utility for that. However, when we use an alcohol instead of water, we don't just use the alcohol to add to the acid chloride. In fact, we add pyridine to the reaction mixture. And the reason why is because when you do these reactions, you end up producing HCl, which is a strong acid, right? Strong acid. And so if you add pyridine, which is a base, and you combine it with HCl, which is an acid, you end up with a salt. So you end up with pyridinium chloride. And so the pyridine serves to neutralize your hydrochloric acid. If you're not following me 100%, let me show you what I mean, okay? If you take an alcohol, okay, and treat it with an acid chloride, you get a reaction where you form an ester, okay? However, you use the pyridine because the pyridine is going to, we say it's mop up, or we're going to say it's neutralizing the HCl formed, and so you're going to end up with pyridinium hydrochloride as well. Now, the mechanism, the whole thing isn't shown here, but it's exactly what you think it is, right? Your alcohol is not a strong nucleophile, but it is a nucleophile, and this is a very powerful electrophile. So the first step is going to be a nucleophilic attack. like this to form a tetrahedral intermediate. Then we lose the chloride and we pick up the proton from this oxygen right here to make our ester. Now, what's cool about this reaction, and there's several things that are cool about this reaction, but one of the things that's cool is if you react an acid chloride with a primary versus a secondary alcohol, it's actually selective for the primary alcohol. Why? Because it's less sterically hindered. So we could put here primary, less hindered. And so it makes a better nucleophile to attack the acid chloride like this. Keep in mind, these are not complete mechanisms that are in drawing here, but it gives us an idea of what's going on. So with that in mind, what would happen if we were to take an acid chloride and treat it with ammonia or a primary amine or a secondary amine? Well, you see here that we have just that. We have ammonia, then we have a primary amine, and we have a secondary amine. And you notice that in each one of these reactions, you need 2 equivalents of your amine. What that means is if you have 1 mole of your acid chloride, that you need 2 moles of your ammonia or your primary amine or your secondary amine. Now, why would you need 2 equivalents? Well, you see that in this case, we don't have pyridine in the reaction mixture, but we know that amines, okay, an amine, whether it's ammonia or a primary amine or a secondary amine, that is a base. And so the first equivalent of the amine is used to do the nucleophilic attack, right, to do the nucleophilic acyl substitution. But the second equivalent of the amine is used to, like I said, mop up the HCl, or another word you could use is neutralize, right? It's used to neutralize the HCl formed in the reaction, and that's why we use 2 equivalents. You know, one of the things that is kind of crummy about this reaction, and I've experienced this firsthand, is that let's say you're doing this reaction with some kind of amine, but it took you 2 weeks to make that amine, okay? If it took you 2 weeks to make that, that means when you put it in the reaction mixture, you know that half of it is going to be gone immediately because half of it is just used to neutralize the HCl that's formed. And so in the case of ammonia, okay, the first one, you would end up with ammonium chloride as your salt. In the second one, you'd end up with the alkyl ammonium chloride, which would be your salt. And then in the last one, you'd end up with the dialkyl ammonium. I'll just put the bonds here explicitly. Chloride, that would be your salt that's used to neutralize the HCl in all 3 of these cases. And so it turns out that there are other reactions that you can do with an acid chloride, okay? If you're not following me, if you're struggling to see where we're going, let's just go back to the beginning, okay? The whole point of this section, 20.8, is to discuss the chemistry of acid chlorides. We've kind of gone through a few reactions. First, we said, okay, you can make an acid chloride by treating a carboxylic acid with thionyl chloride. Then we said, if you take an acid chloride and you put it in water, just pure water, well, that's just going to hydrolyze the whole thing right back to the carboxylic acid. But if you tried to do this with an alcohol, right, an alcohol instead of water, in that case, you would add pyridine because you'd need that to neutralize the HCl. And that's what you see in both of these reactions. We're taking an alcohol plus an acid chloride plus pyridine to give us an ester in both of these cases. Then we said, okay, what happens if you react an acid chloride with an amine? Well, if it's an ammonia, you end up with what's called a primary amide. If you react it with a primary amine, you end up with what's called a secondary amide. And if you react it with a secondary amine, you end up with what's called a tertiary amide. If you're still unsure what primary, secondary, and tertiary amide refer to, you've probably figured it out just in the time it's taken me to say that when it's primary, your nitrogen is attached to 1 carbon. When it's secondary, your nitrogen is attached to 2 carbons. And when it's tertiary, yes, your nitrogen is attached to 1, 2, 3 carbons. Okay? And the reason why we use 2 equivalents of the amine in each one of these cases is to neutralize the HCl that is formed. We don't neutralize the HCl when we're just using pure water, but if we're using an alcohol, then we do need pyridine to neutralize that HCl. All right, moving forward, what about the reduction of an acid chloride? Well, it turns out that you can reduce an acid chloride with this reagent that you've seen way back in the alcohols chapter. We call this lithium aluminum hydride. So if we take lithium aluminum hydride, so LAH, okay, and you should remember the Lewis structure of the aluminum hydride is shown down here on the bottom left. When you treat an acid chloride with excess lithium aluminum hydride followed by water or H3O plus, either one is fine, you end up with a primary alcohol. So pay close attention. Acid chloride, where am I here? Acid chloride, LAH, gives you a primary alcohol. And the mechanism is shown down here. I'm going to put a red star by this because I think it's important that you understand this mechanism. There's kind of two parts to it. The first part is a nucleophilic attack by the aluminum hydride on your acid chloride. So this is your starting acid chloride, okay, which is very reactive. And aluminum hydride is a very reactive ion. So it delivers the hydride and we end up forming the tetrahedral intermediate. Now you guys know that chloride is an excellent leaving group. So we lose chloride. So we could even write here minus Cl minus, loss of chloride. And then what do you notice? Lo and behold, now we have an aldehyde, okay? And what do we know? What happens when you put an aldehyde in the presence of lithium aluminum hydride? That's right, you get a primary alcohol. So this second part of the mechanism here, this was actually covered in chapter 12, in the alcohols chapter, okay? So our aldehyde undergoes a nucleophilic attack by the hydride. You form a tetrahedral intermediate, and then in the last step, again, you can write water, but generally speaking, we write H3O plus. It protonates the alkoxide, and you end up with your primary alcohol. Again, I don't want to say simple because that word doesn't belong in organic chemistry, but I'd say a relatively straightforward mechanism here. Now, here's something completely new. Okay, today is June 10th. Here's something completely new that we've never ever discussed before. It turns out that you can actually take an acid chloride and reduce it to an aldehyde, but you can get it to stop right here. Okay, you can get it to stop here and react no further. Now, how do you do that? Well, to do that, we're going to need a new reagent. And for that, we use something called lithium tributoxy aluminum hydride, which is this guy here. I know it's a bit of a mouthful to say that, lithium tributoxy aluminum hydride, but you can just use the acronym. I guess it's not really an acronym, but instead of writing the T-butyl group, we just write an R group like that. So keep in mind that this is an R group, this is an R group, and this is an R group. So you see how we have three R groups, or three OR, OR, and OR groups, okay? So we say lithium, aluminum, tributoxy. So we put OR, 3, and then there's one hydride ion, okay? So since there's only one hydride ion, it's going to reduce the acid chloride down to the aldehyde, and it stops there. So it reacts no further. So you can put a big X. It's not going to react any further from there. Now in the second step here, I put water. You could also use hydronium. Either one is totally fine, but this is a brand new reagent. And so it says here at the bottom that this reagent, the lithium tributoxy aluminum hydride, is more selective and reacts with acid chlorides faster than aldehydes, so the aldehyde can actually be isolated. So pretty cool. Now we've got two options. We can either reduce our acid chloride with lithium aluminum hydride, followed by treatment with H3O plus, right? That's going to give us a primary alcohol, but if we use the more mild reducing agent, the lithium tributoxy aluminum hydride, that reduces it down to the aldehyde after our workup with acid. So this reaction is not a review, but this is similar to the reaction that we saw between a Grignard reagent and an ester back in the alcohols chapter. So to review, I'll just put here, similar to an ester with Grignard reagent. Okay, it's a similar reactivity. If we take an acid chloride and treat it with excess Grignard, followed by treatment with water or aqueous acid, either one is fine, we end up with a tertiary alcohol in this case. And this mechanism, it says here, is analogous to the reduction with lithium aluminum hydride. And so therefore, we think it is a pertinent mechanism for us as Chemistry 3111 students. The first step, you remember that Grignard is not only a strong base, but it's an excellent nucleophile. So it's going to attack the electrophilic carbon, this one here. That's where your big old delta plus is. You form the tetrahedral intermediate. Well, you know that this is not a good leaving group, but chloride certainly is a fantastic leaving group. And so we lose our chloride ion, and then we end up forming a ketone. And you guys know what happens when you react to ketone with a Grignard. The Grignard is going to undergo a nucleophilic attack. We get this tetrahedral intermediate shown here. And then in the very last step, we treat it with our aqueous acid shown here. We do the proton transfer, and there you go, a tertiary alcohol. So you're seeing how synthetically useful an acid chloride. Well, we got a couple more reactions to go. The next one is, if you're wondering, is there a way for me to stop the reaction here? Could I just stop it at the ketone somehow, analogous to the way I stopped the reduction of the acid chloride at the aldehyde? And the answer is yes, but we don't use lithium tri-T-butoxyaluminum hydride. In this case, we use something called a Gilman reagent, okay? A Gilman reagent or a cuprate, okay? So sometimes I'll say Gilman, and other times I'll call it a cuprate. They mean the exact same thing. So a cuprate is shown here, okay? And there's no mechanism supplied in our textbook for this reaction whatsoever, absolutely nothing, okay? But the way the cuprate works is that you have the copper bound to two R groups, and that gives it a negative charge, and then you have your lithium cation like that. So we call it a lithium dialkyl cuprate, and it turns out that the R groups here, okay, are less nucleophilic than the R group from a Grignard, and so it only adds once to the acid chloride, and you end up forming a ketone. So we would call this, you could call this lithium dimethyl cuprate. So you could call this lithium dimethyl cuprate. Okay, but I'll just be honest, I'll probably give it some other goofy name, like I'll call it like a methyl Gilman or a methyl cuprate or something like that. But they always are the same thing. Okay, whatever your alkyl group is in your Gilman reagent, that is what's going to add onto the carbonyl like that. And again, I'll even write it down here for you that there's no mechanism that you need to know for the Gilman reagent stopping at the ketone. So now, what have we covered? Okay, we've covered a lot of information, but the bottom line is that every one of these reactions started out with an acid chloride. Okay, what did we first look at? Well, first we said you could take the acid chloride and you could just treat it with water. You don't necessarily need pyridine, but pyridine can be used. Okay, so we'll put here neutralize HCl. It's not that important with water, but they put it in here, so we'll say it counts, okay? We also said that you can synthesize the acid chloride using thionyl chloride. Okay, so what have we got so far? We've got synthesis of the acid chloride. You can blow it apart in water with some pyridine. You can do an alcoholysis reaction, which means you react it with an alcohol and pyridine, and then you end up with an ester. Then we said, okay, well, you can treat it with ammonia or a primary amine or a secondary amine. And if you do that, you end up with a primary, secondary, or tertiary amide, respectively. Remember, you have to use excess in each one of these. The first one is to do the nucleophilic acyl substitution. The second equivalent of your amine, and remember, amines are bases, is to neutralize the HCl. The next one was reduction with lithium aluminum hydride, followed by treatment with water or hydronium, either one is fine, to give you a primary alcohol. So you can put here primary alcohol. If you wanted to stop at the aldehyde, you would use this. So lithium, so it's lithium tri-T-butoxy, butoxy aluminum hydride. It's a mouthful for that reagent, but that's going to stop at the aldehyde. And again, in the second step, you could put water or H3O plus. Either one is fine. The next one is the reaction of the acid chloride with the excess Grignard, followed by treatment with water or aqueous acid. And we said that that was analogous to the reaction of an ester with excess Grignard. In the last one, this is the Gilman reaction or the Gilman reagent or a Gilman reagent, I guess. So this would be some kind of lithium dialkyl cuprate is what we called it. And that stops at the ketone, okay? Now, before you get too stressed about all these reactions, like, well, that's a lot of reactions for me to learn. It is, Okay, but what you're going to see is that the good news is that when we get into acid anhydrides in the next section, when we study anhydrides, so you guys remember what an anhydride is, you're going to see a very similar reactivity for anhydrides that we do for acid chloride. So now that we've got all that information in our short-term memory, let's take a look at a couple of reactions. Now, it's not asking us to draw any mechanisms here, so let's just see if we can come up with some major products, okay, for each one of these reactions. Now, in the first one is treatment of an acid chloride with lithium aluminum hydride, followed by treatment with water. And again, here you could put or hydronium, either one is fine. Could anybody tell me what kind of functional group we're going to end up with in the product? And it's not a trick question or anything. Yeah, Eric, 100%. We're going to end up with an alcohol. Yes, we're going to end up with an alcohol. Does anybody remember, will it be primary, secondary, or tertiary? When we reduce with lithium, it's going to be a primary alcohol. Thanks, Rachel. Perfect. So I think one of the things that I've noticed, because I've actually asked this exact question on a quiz before, and I think that where my students sometimes would struggle is in counting the carbons. So you want to make sure you've got 1, 2, 3, 4, 5 total carbons. So we count them very carefully. 1, 2, 3, 4, 5. So that means the alcohol is going to be attached over here. Okay, so we end up with a primary alcohol. Thanks, you guys. All right, the next one, we're taking our acid chloride and we're treating it with excess Grignard, followed by treatment with water. So this is phenylmagnesium bromide, followed by treatment with water. And again, you could put or H3O+. Now, what's cool about this one is that the nucleophile, your phenyl Grignard, is going to add the first time, and you're actually going to end up with this compound. So this is actually going to be your intermediate along the way. It's not the final product. Maybe I should erase this. I'll just put phenyl just to save some real estate here, okay? So we end up with a ketone as an intermediate. That's what these square brackets represent, that this is only an intermediate, because then the ketone is going to react again with more Grignard, and so we're going to end up with an alcohol. Could anybody tell me what type of alcohol we're going to end up with in this case? What kind do you end up with in this case? What kind of alcohol? It is a tertiary alcohol. Okay, so we end up with a tertiary alcohol in this specific case. And then in the last one, we're reducing an acid chloride with lithium tri-T-butoxy aluminum hydride. And so after step one, if you remember, and if you forgot, let's go back and take a look. Okay, we take our acid chloride and we treat it with lithium tri-T-butoxy aluminum hydride. We end up with an aldehyde. So that's in step one. So let's draw the aldehyde that would be formed. It's going to be cyclohexane carbaldehyde. That was one of our nomenclature examples. So that's after step one. Then after step two, we're going to treat it with ethyl magnesium bromide, followed by treatment with water or H3O+. So if it's not excess, right, it's only going to add once. So that means we're going to add our ethyl group. So we're going to end up with, there's the carbon that's been there the whole time. Then we have an ethyl group. So we have our, we have our alcohol, and then we have 1, 2 carbons like that. So there you go. All right, so we end up with a secondary alcohol in this case. All right, give me a thumbs up if you follow me even like 40% of the way. Well, I'd say 50%. You guys are all very astute at mechanisms at this point, okay? So let's go back and review. What did we cover? We covered formation of an acid chloride with thionyl chloride. You can blow it apart with water. I don't know why you would do that, but it's in there, okay? You can form an ester. We call this alcoholysis, okay? You use pyridine to neutralize the HCl. If you do the reaction with ammonia, a primary or a secondary amine, you end up with a primary, secondary, or tertiary amide. You need excess because the second equivalent is there to neutralize the HCl. Reduction with lithium aluminum hydride affords a primary alcohol. Reduction with lithium tri-T-butoxy aluminum hydride gives you the aldehyde. treatment with a Greenyard in excess gives you a tertiary alcohol. And then if you use a Gilman reagent, that's going to stop at the ketone. That's just going to add one time, and then it stops there. The buck stops there. All right. So now that we've got that down, that kind of covers the chemistry of acid chloride. So now we're going to get into anhydrides. And if you remember, towards the end of the last lecture, we said that acid chlorides were the most reactive of the carboxylic acid derivatives. And then we said anhydrides were the second most reactive. Now, if we compare these two, okay, if you compare an acid chloride and an anhydride, right, they both have carbons that are susceptible to nucleophilic attack, right, because there's electron withdrawing groups attached to them. What's the big difference? I'd say it's this. With an acid chloride, the leaving group is chloride, which is the conjugate base of a strong acid, whereas here your conjugate base is going to be some kind of carboxylate, which is the conjugate base of a carboxylic acid, and carboxylic acids aren't strong acids. And so we don't produce any strong acids like HCl. Now, to backtrack a little bit, if you're wondering, where do we get anhydrides from? How do we make them? Well, there's a few ways to make anhydrides. But if you want to make a symmetrical anhydride, so like acetic anhydride, all you have to do is take acetic acid and heat it up. So this is a very specific reaction, specific to acetic anhydride, which is a very common reagent in organic chemistry. It's actually used to make Tylenol and aspirin. But anyhow, if you take acetic acid and just heat it up, well, that pulls the water out of it, and you end up with acetic anhydride. But again, most acids can't survive this kind of extreme temperature. I mean, 800 degrees Celsius is pretty warm. So a more practical synthesis of an acid anhydride is to take an acid chloride and react it with some kind of carboxylate, right? You guys know that this is a carboxylate. It's the salt from a carboxylic acid. And you can imagine that this is a good nucleophile, and this is a good, well, that's not a very good curved arrow, but this is a good nucleophile, this is a good electrophile. And so we're going to get a nucleophilic attack, and we see that nucleophilic attack drawn right here. We form the tetrahedral intermediate. Now we lose our chloride ion as our leaving group. Why? Because this chloride is a better leaving group than losing a carboxylate. And so we end up with an anhydride. So let's repeat that, okay? If you want to make acetic anhydride, and acetic anhydride is a very common reagent, okay? All you have to do is take acetic acid, which is abundant and cheap, and heat it up to 800 degrees Celsius. And you're going to end up with acetic anhydride. But most carboxylic acids can't be heated to 800 degrees Celsius. So what do? You'd make the acid chloride, and then you treat it with the carboxylate salt. You have a nucleophilic attack, loss of leaving group, bada boom, bada bing. There you go. You have just made your anhydride. Okay. So now, like I was trying to tell you before, is that the leaving group in an acid chloride is chloride, which is the conjugate base of a strong acid, okay? Whereas the leaving group over here is going to be a carboxylate ion, which is the conjugate base of a weak acid. And so it's not going to be as good a leaving group, but it's also it also doesn't produce a strong acid, and so we don't have to use pyridine for reactions that involve an anhydride. Why? Because we don't form a strong acid in the end. So let's take a looky here. So here are some reactions of acid chlorides. Maybe I should go back here, okay, and we'll write down the conjugates. So HCl has a pKa that's equal to -7, whereas a carboxylic acid just write has a pKa of approximately 5. So maybe that'll help clear it up for somebody. But anyhow, if we take a look here, all right, yeah, where was I? Let's see here. So figure 2.10 shows how anhydrides can go many reactions analogous to those for acid chlorides. Okay, so now we're kind of repeating what we saw with the acid chlorides, but now we have an anhydride. Okay, so follow along with me. The first one is if you want to make an acid anhydride, well, you got a couple of options. If it's just acetic acid, acetic acid. In that case, you can just heat it up to 800 degrees Celsius, and that's going to give you acetic anhydride. However, if it's something bigger, in that case, you're better off to use sodium hydroxide to make the salt, and then you react it with the analogous acid chloride. You get the reaction that I showed you right here. Okay, that's this reaction right here. Okay, so we've covered those. Then, much like a acid chloride, if you put a anhydride just in water, it's going to hydrolyze back to the carboxylic acid. Now again, no pyridine is used in these reactions, right? In this one, we don't use pyridine. Why? Because we don't end up forming HCl. So I'll put here no pyridine because HCl is not a byproduct. Okay, it's a byproduct when we have an acid chloride, but it's not a byproduct when we use an anhydride. We end up with a carboxylic acid in that case, which is a weak acid. So if we do the alcoholysis, we just need our alcohol. Leaving group leaves, we do a proton transfer, and we end up with an ester. If you have ammonia, a primary or secondary amine, you're going to end up with a primary, secondary, or tertiary amide, respectively. And in each one of these cases, we end up with excess of the amine to neutralize in the end. If you treat an acid anhydride with lithium aluminum hydride followed by water or H3O+, it reduces to a primary alcohol. If you use lithium tri-T-butoxy aluminum hydride followed by water or hydronium, you end up with an aldehyde. If you use excess Grignard followed by treatment with water or hydronium, you end up with a tertiary alcohol. And if you use a Gilman, remember this guy here, the cuprate, and you can call it a cuprate, that's fine. In fact, we do a lot of the time, we just call it a cuprate or a Gilman, you end up stopping at the ketone. All right, so give me a thumbs up if you're with me on that. You're like, all you did was go over the same reactions. Well, there's a couple of nuances here, a couple of them, not in abundance, but there are a couple of them here. So before we move forward, let me show you something interesting here. So remember I told you that you could make acetic anhydride, this compound here, by heating up acetic acid to 800 degrees Celsius. Well, it turns out that acetic anhydride is actually a very common reagent, okay? It's used to put an acetyl group on an alcohol or an amine. If you put the acetyl group on an alcohol, right, then you end up with an ester. So in this case, you end up with an ester. And if you add it to an amine, you end up with an amide. You're like, hey, I recognize those functional groups. And like I told you, acetylation using acetic anhydride. So again, this is acetic anhydride here. This is acetic anhydride here. It can be used to put an acetyl group on a hydroxyl or an amine. So if you put it on this hydroxyl, you end up with acetyl salicylic acid, which is aspirin. And if you put it on the amino group of para-aminophenol, you end up with paracetamol, which is also known by its trade name, which is Tylenol. So understanding acetylation is a very important reaction. In fact, it's the acetyl group that blocks the synthesis of prostaglandins, which cause inflammation, which makes us feel better when we take an aspirin. So let's take a look at these two reactions here, okay? The first one says we're going to take this benzoic anhydride. So that's what we would, so right, if we have benzoic acid, if you had a hydrogen here, there would be benzoic acid. So this would be benzoic anhydride. If we treat that with phenol, what are we going to end up with? Okay, what we're going to end up with in that case is we're going to end up with, and I'm just going to draw a partial mechanism here, is the hydroxyl is going to attack the carbonyl to make a tetrahedral intermediate. And then we're going to end up replacing or losing, this part is our leaving group. So all of this is going to be our leaving group. So we'll put leaving group here. So what do we end up with? We're going to end up with our aromatic ring, and we have our carbonyl followed by our oxygen with our aromatic ring from our phenol, like that. Now, if you're wondering, well, what else do we get? What else do we get from that leaving group? The leaving group is going to give us this. Okay, so we're going to end up with the leaving group, but again, it's not going to form a strong acid, it's going to form a weak acid, which is going to be benzoic acid. So these are the products that we're going to get in this case. All right, with the next one, we have, what would this be? Propionic anhydride or propanoic anhydride, either one is fine. We're treating it with this is called diethylamine. We're using XS, right? The first equivalent is to do the nucleophilic attack. The second one is to neutralize the acid that's formed. So in that case, we're going to end up with our propionyl group. So that's going to look something like this, but now we're going to have a secondary amide. So we're going to end up with something that looks like this. So we call this NN-diethylpropanamide. Plus, we're going to end up with the carboxylate, that, and we're also going to end up with the ammonium ion like this. Okay? Now, before we go any further, if you're struggling with this, when do I need a base? When do I not need a base? Okay, let me show you. If we just go to a blank document here, okay, I'll kind of walk you through it here. So what's going to happen is this. If we go back to the reaction of an acid chloride with an alcohol, so if I react an acid chloride with an alcohol, so just put ROH here. Remember, I said that you have to use pyridine for this reaction. Okay, so let me go through the explanation as to why. Okay, so again, the first step is going to be our nucleophilic attack, like this. We are going to form a tetrahedral intermediate, which is going to look like this. We have our negative charge here, we have our chlorine here, and then we have our oxonium from our alcohol that attacked like this. The next step is going to be loss of our leaving group. So we're going to lose the chloride ion as our leaving group. And when we lose that chloride ion, we're going to end up with something that looks like this. So we still have a charge on this oxygen, and then we have the chloride ion over here. So then what's going to happen is that the chloride ion is going to pick up that proton. So the chloride ion can, oops, where's my red pen? Can pick up that proton like this, and then we end up with our ester plus HCl, okay? It's a bad thing to have HCl in our reaction mixture, okay? The reason why is because HCl, if there's any water present, it'll form hydronium, and it can actually hydrolyze the ester. So we'll put here bad for reaction mixture, okay? And then we'll put here since this is a strong acid. We don't want to have strong acids left over in our reaction mixture. So then what we do is this. Let me just redraw my HCl in a bond line structure like that, is we have pyridine in the reaction mixture. And the pyridine is a base. Okay? And so it's actually going to pick up the proton from the HCl. And so now you end up with your ester. It's intact. It's totally fine now. Okay? It's got no HCl around to bother it because it's all been converted to the pyridinium hydrochloride. So this is called pyridinium and then hydrochloride, like that. And so that's a salt, and so that's relatively innocuous. It's not going to hurt anything. So now your ester, there's nothing around that's going to damage your ester. Your ester is going to stay intact. If you had HCl in there, it's probably not going to last. So now, if we try the exact same kind of reaction, but we use an anhydride, I'm going to explain to you why we don't need pyridine. Okay? So now we're going to do the very similar reaction. So I'm going to take an anhydride. So if we draw an anhydride, it looks something like this. Okay, and if we treat that with an alcohol, now I said we do not need pyridine. So we'll put here no pyridine. Okay, so what's our first step going to be? It's going to be our nucleophilic attack. Okay, and then we're going to form this intermediate. We have our negative charge here, our oxygen. This is going to be our big old leaving group over here. And then we're going to have our oxonium, something like that. Not my best artwork, but not my worst. So we're going to lose our leaving group now. But keep in mind, the leaving group is not the conjugate base of a strong acid. The leaving group is the conjugate base of a weak acid. So we're going to end up with this where we have our oxonium like this, plus we end up with a carboxylate. Okay, and again, this is the conjugate base of a weak acid. So what's going to happen now is that the carboxylate is going to pick up this proton to neutralize. Okay, and then after that, oops, my arrow's going in the wrong direction. Okay, there we go. After that, we're going to end up with our ester, that plus a carboxylic acid. Okay, but the carboxylic acid is of no harm whatsoever. Okay, so I'll just move it over here and say we get our ester, but again, this is a weak acid. Okay, will not destroy or degrade or break down the ester that's formed. So everything's going to remain intact. So that is my explanation as to why when you use an acid chloride, you have to have pyridine. It's to get rid of the HCl. HCl, bad for your reaction mixture. Whereas when we have an acid anhydride, we don't need our pyridine now because we end up forming a weak acid. Not dangerous whatsoever, right? Carboxylic acids are acids. They are proton donors, but they certainly aren't strong acids. Okay, I'm not going to ask you for a thumbs up on that, but I hope, actually I will. Does that clear it up for anybody? Does that shed some light on the subject? Because I feel like the textbook doesn't go into too much detail on that. And maybe I go into too much detail, but I don't want you to be coming out and saying like, why, why is this happening? Why do I need this? Okay. So now that we've uncovered all of this, okay, we've covered all the reactions of anhydrides. We covered acetylation with acetic anhydride. We saw how this is used to synthesize aspirin and Tylenol. We took a look at these two reaction mechanisms here. So before we get into esters, what I want to do is I want to go right back to the beginning of the class today because we didn't solve these problems here. Now, I'm sure you guys can do these in your sleep without any help from this guy, but let's just take a quick peek at them. So the first one is an acid chloride, and it's the reaction between an acid chloride, let's see here, acid chloride and a carboxylate ion. So we have our carboxylate ion, which is a good nucleophile. We have our acid chloride, which is a good electrophile. So let's start with our nucleophilic attack, and I'm not going to redraw anything here. I'll just try to add in some dots here for my electrons. So actually, you know what? Why don't I just use this? I'll use the negative charge, and I'll do my nucleophilic attack like this. And let's draw the intermediate that's going to be formed. So we're going to end up with something that looks like this, where we have a negative charge on our oxygen. We have our chlorine, which is going to be our leaving group. We have our, you can see we're going to form our anhydride. So we end up losing the leaving group. So we'll lose chloride ion like that. Hopefully you can see that curved arrow like that. There we go. And so after that, we're going to end up forming our product. Plus, you notice that we have the sodium cation and we lost chloride. So we're also going to have sodium chloride in that case. All right, with the next one, we have our ammonia, which is going to be our nucleophile. We have our good electrophile, our acid chloride. So we do a nucleophilic attack. Let's draw the intermediate. So it's going to look something like this. So we have our negative charge here, our chlorine here, and now we have NH3 like that. So now we're going to lose our leaving group. We're going to lose the chloride like that, and we're going to end up with our, going to be closer to our amide, which looks like this, okay, but we still have that positive charge on our nitrogen. And so now we have our chloride ion, and the chloride ion could pick up this proton to make HCl, but it's not as strong a base as ammonia. So ammonia is a stronger base, and remember, we're doing this in excess ammonia. So what's going to happen is the ammonia is going to pick up the proton like this, okay, because ammonia, again, is a good base. And then we're going to end up with the product, okay, plus we're going to end up with ammonium chloride, right? So remember, we have no HCl because the HCl, right, HCl plus ammonia gives you ammonium chloride, right? It's going to lie to the side of the weaker acid. This is a strong acid. This certainly isn't. So there you have it, my friend. So that is why we use an excess, and I should put here excess of ammonia in this case. All right, so that covers the reactions of acid chlorides. Didn't mean to do that. So we've gone over the reactions of acid chlorides in detail. Then after that, we covered all these reactions. Then after that, we looked at the reactions of anhydrides, which are very similar. We talked about when we need pyridine, when we don't need pyridine, why we need pyridine as a base with an acid chloride, why you don't need it with an anhydride. We talked about why excess of your amine can neutralize the HCl. We talked about acetylation. We went over these mechanisms, and that brings us to the section on esters. Now, we're going to take a break now, but before we get into it, there's a few things that you're going to learn in the section on esters that I want you to kind of meditate on, okay? Some of the most important mechanisms in all of organic chemistry are found in this section. One of them is Fischer esterification. That's the formation of an ester, and then an ester can be hydrolyzed two ways, okay? It can be hydrolyzed in acid, and it can also be hydrolyzed in base. And both of those are important mechanisms as well. So we're going to look at the mechanism of Fischer esterification, then hydrolysis in acid, and then hydrolysis in base. And when you have the hydrolysis done in base, it's got a special name. This is called saponification, and it's a very widely studied and tested concept in organic chemistry. All right.